Hello everyone, my name is Aditya Lahiri and I'm going to take you through this first section of the tutorial. We will talk in depth about feature-based explanations. So let's get started. First off, we would like to spend a little bit of time understanding this dataset which will be used throughout the tutorial. This is the adult dataset, which is also known as the income or census income dataset. It is publicly available on the UCI data repository. The predictive task which is performed using this dataset is to classify whether an individual would earn more than $50,000 a year based on the attributes obtained from a census. It has 14 attributes that are a mixture of categorical and numerical types. We have a few examples listed in this dummy table to get a better understanding of what the data looks like. We can see that we have features corresponding to age, education level, race, marital status, and so on corresponding to an individual. The label is the income column, which tells us whether the individual's income is greater than or equal to 50K or less. Now we consider the following loan decision scenario. We have a bank that uses machine learning models in its decision-making process of granting loan to its customers. Rosa is one such hypothetical customer. There are other customers of the bank as well. We have Rosa's data, which states that she is age 34, has a bachelor's degree, works 40 hours a week, and so on. Her attributes are fed into a black box machine learning model which spits out its prediction. Here, the model predicts with 83% probability that Rosa's income is less than 50K. The manager in the bank has to use this prediction made by the model as part of her loan decision. However, since this is a black box model, the manager is confused about how the model arrived at this prediction. In addition to this, if the bank declines Rosa's loan, she would also like to know the reasons behind the denial. Therefore, it is essential to understand the reasoning behind the black box model's prediction, both for the bank and the end user. We will now go over a broad class of explanations called feature-based explanations. These forms of explanations attempt to provide a reasoning behind the model's decision-making in terms of the features that are provided as input to the model. These feature-based explanations can be divided into two broad categories. In case of real valued attributions, a number is assigned to each feature, indicating its contribution to the final prediction. These real valued attributions can be causal or non-causal in nature. On the other hand, explanations can also be presented in the form of rules that are composed of different features. If an instance follows the provided rule, then it will have a certain outcome. We begin with a popular feature-based explanation called line. Line provides real valued attributions as explanations and is non-causal in nature. Line works on the underlying principle of using simple surrogate models to explain complex black box models. Let us try to understand what this idea is. For purposes of easy visualization, suppose that we build a model using only two attributes from the adult dataset, age and education level. We train a random forest model, which is a complex model and not easy to interpret. This can be seen through the decision boundary of this model, which is plotted here. It is highly nonlinear and not at all simple. Say that we want to understand the prediction made for the instance marked through the blue dot. To do so, we can look at the small neighborhood around this point and train a simple interpretable model such as a linear model on this neighborhood. Since we are only looking to model a small locality of the entire global decision space, a simple model would be able to do a good job fitting to this data. We can now zoom into the neighborhood around the point of interest and use the inherently interpretable nature of the simple surrogate model to explain its decision making for this instance. We can see that this view is much simpler with the two classes separated by a linear boundary. We can also use the linear model's coefficients to understand each feature's contribution. To summarize, the central idea is that we need complex black box models to learn complicated decision spaces. However, if we are focused on understanding the decision making for one instance, we can simply zoom in to the vicinity of that instance in the decision space. We then mimic the black box model's behavior in only that locality by using simple surrogate models, which are explainable by default. Given this background, we can now look at the relatively straightforward algorithm that Lime uses to generate explanations. First, Lime takes the instance to be explained as input and generates a neighborhood around that instance. It does so by adding perturbations to the dataset through random normal noise. To provide more weightage to points in the vicinity of the input instance, it then weighs all the perturbed instances by proximity to the input instance. The closest instances are assigned greater weight than the instances that are far off from the input instance. This is achieved specifically through exponential smoothing function. Finally, Lime chooses a weighted linear regression as the choice of surrogate model. Lime also adds L1 regularization to this weighted linear regression model in order to enforce sparsity. The coefficients of this weighted lasso regression model are provided as real valued feature attributions to the end user. However, there are some significant issues with Lime. For example, if we take two instances that are very similar to one another, we can get drastically different explanations. Here, we have Rosa and Emma, who are identical in every respect, except that Rosa works 40 hours while Emma works 30 hours. When we run Lime for these two instances, we get different set of feature importances. In particular, if we were to look at the overlap of most important features for these two nearly identical input instances, we would observe that even in the top 5 most important features, there is only 30% overlap. In fact, we do not have more than 50% agreement amongst the top features until we have considered 50 top features. This instability and fickleness is a cause of concern. As an alternative to real valued feature attributions, there have been several works which attempt to provide rules as explanations. These are often more intuitive than assigning real numbers to each feature. In particular, we will look at two rule-based techniques, anchors and MUSE. Let us start with anchors. Anchors provides us with rules that are local sufficient conditions which explain the prediction. These rules provide clear coverage, that is, clear conditions when the explanation will hold. The rules are learned such that they are precise, that is, accurate. For instance, for Rosa's prediction from the black box model, anchors would produce an explanation like so. If R is less than 50 and marital status is not equal to married, then label is less than 50K. This rule informs us that these two conditions have led to the prediction. Now let us revisit the scenario of Emma and Rosa to highlight a key aspect in which Lime and anchors differ. Recall that they were almost identical and varied only in the number of R's. If we see through the lens of the manager, once we run Lime to obtain explanations for Rosa, we are still unclear as to whether this explanation for Rosa should hold for Emma, who is very similar to her. Specifically, if we know from Lime's explanation that top 3 features for Rosa's outcome were age, education, and R's, can we comment anything about Emma's prediction, who is very similar to Rosa? The answer is no. This is because there is no well-defined scope of explanations provided by Lime. They are just applicable to the specific instance and does not allow us to understand even instances very close to them. However, this issue is resolved through anchors. The rule-based explanation given by anchors is a valid explanation for both Rosa and Emma in this case, since both of them satisfy the rule. This also means that the rules that anchors provides as explanations are more robust and applicable to similar instances, which was not the case in Lime. Anchors attempts to provide high-quality rules. The quality is governed by two specific metrics, precision and coverage. Let us look at 3 candidate rules that could be valid explanations for Rosa's prediction. If we move through the topmost rule to the one at the bottom, we can state that precision of the rule increases. So what is precision exactly? If the rule states that on satisfying its conditions, you will have a particular outcome, say less than 50K, and that claim is correct, then the rule is said to be precise. As we move from top to bottom, with increasing complexity in the form of additional clauses, the rules are becoming more accurate and precision is increasing. On the other hand, if we move from the bottommost rule to the top, coverage is increasing. Coverage captures the applicability of the rule. The more relaxed a rule is, the more widely applicable it is, and the higher its coverage is. Very specific rules with large number of clauses have low coverage due to being applicable to a very small subset of data. A good rule will have both good coverage and precision. That is, it would be applicable to a sizable subset of data and would also be correct in its claim of the output label for those data points. So how are these rules computed in anchors? They formulate this as a multi-armed bandit problem and use beam search to obtain a bottom-up construction of high precision rules with maximum coverage. Let us now look at another rule-based explanation technique called MUSE. It is different from both Lime and anchors in that it is a global explanation method. This means that it is not trying to explain the prediction for one specific instance. Instead, it is trying to give a high-level global understanding of the entire decision space of the black box model. The way MUSE approaches this global understanding is by breaking down the entire decision space automatically into relevant subspaces. Let us look at the same example from the section on understanding surrogate models when we use two features, education and age, to model income and trained a complex random forest model on it. In contrast to focusing on zooming in on a neighborhood around a specific point like Limewood, MUSE tackles the entire decision space. It divides the decision space into subspaces by defining the subspaces through learned rules. It then provides nested rule-based explanations corresponding to each subspace. Hence, what we get is a two-level, rule-based global explanation of the entire black box model. Let us look at the kind of explanations that MUSE generates. It takes the entire dataset as the input instead of one single instance to provide global, two-level, rule-based explanations. It provides users with these nested rule-based explanations. The relevant subspace is defined by the outer rule. Now, for instances that satisfy the outer rule, the applicable explanation can be obtained from the internal nested rule corresponding to that subspace. Hence, the explanations are two-level rules. So, instead of flat rules provided by anchors, MUSE provides hierarchical rules for global level model understanding. MUSE obtains these rules by jointly optimizing for fidelity, unambiguity, and interpretability of the generated rules. Fidelity refers to how accurate the rules are. Unambiguity refers to mutual exclusiveness of rules. In other words, one instance should not have more than one rule applicable to it because this would lead to ambiguity. Interpretability is optimized so that generated rules are more human-friendly. Shorter rules are considered to be more interpretable than longer rules, and MUSE tries to generate shorter and more interpretable rules by directly optimizing for them. Let us now pause for a moment and briefly look back at what we have covered till now. We motivated the need to understand the decision-making process of a black box machine learning model that is being used as a factor in deciding loan request outcomes in a bank. We looked at two broad categories of feature-based explanations, one that assigns a number to each feature and the other that creates a rule based on feature values to justify the prediction. We looked at three specific methods, line, anchors, and MUSE, that can be used to generate such explanations. However, all these explanations obtained till now have been guided more by intuition than by rigorous axioms and do not carry with them any mathematical guarantees. What we will look at next will be a framework that tries to first set out a list of desirable properties that an explanation should have, and then borrows a specific technique from game theory to obtain explanations that satisfy those properties. That being said, let us now look at Shapley values-based explanation techniques that seek to achieve this principled and axiomatic approach towards generating feature attributions as explanations. We once more consider the now familiar case of the model's prediction on Rosa's data. We see that it is with probability of 0.83 that the model states that she would earn less than 50K per year. The feature attribution values produced by standard surrogate model-based techniques such as line are not bounded. They are simply the coefficients of linear models in case of line, and they are not constrained in any manner. A desirable property of these feature attributions would be if they could add up to something meaningful and be bounded. Specifically, it would be useful if the feature attributions would add up to the prediction. That way, we could see this as a decomposition of the prediction to the respective input features. It would also be useful to have sufficient conditions for when the feature attribution would be zero for any specific feature. This is useful to detect redundant or non-informative variables in a model's decision. Further, we would also like to have similar feature attribution values for two features that behave similarly with respect to the black box model. Shapley values formalize these three desirable properties as axioms. They are called the efficiency, null, and symmetry axioms, respectively. Shapley values is a concept from game theory and is named after its creator, Lloyd Shapley, who was a Nobel Prize winning economist and contributed heavily to the field of game theory. Shapley values provide a unique solution for decomposing the payoff from a cooperative game to its individual participants while following the three properties we discussed. Those form a part of the axioms that Shapley value-based allocation satisfies. Let us try to understand vanilla Shapley values first, and then we will link them to explainable AI. We begin with some simple game theory terminology that will help us understand Shapley values. A coalition is a set of players participating in the game. Null coalition is a specific type of coalition that has no players. Grand coalition is a coalition containing all the players. So in this case, we have 4 players playing the game, and since all 4 of them are in this coalition, it is the grand coalition. Furthermore, we define capital S to be the set of players that are considered to be in coalition. Here, these 2 players are in coalition. S prime is the set of players out of coalition. All members from the grand coalition that are not in S are in S prime. S union S prime will always be equal to the grand coalition. We will also need to define something called a value function. The value function tells us the score if the members who were in coalition had played the game. In this case, if 2 members in S had played the game, they would have scored 10 in this particular game. Now that we have a good understanding of the terminologies, we can look at a concrete toy example. We have 2 players, P1 and P2, who are playing table tennis. They may play alone, 1 versus 1, or in a team. They want to know who the better player is among them. We can use Shapley values to solve this dispute in a principled way. Based on the games that we have played, we have the following data. If player 1 played alone, they scored 6. If player 2 played alone, they scored 8. When player 1 and player 2 played together, they could score 12. And when none of them played, the score was 0. Given this data, we can use Shapley value formula listed here to compute the individual payoffs. This is just a weighted sum of marginal contributions of the ith player across all possible coalitions. Now don't worry, we won't just skip over this slide right now. Let us break that down. We are computing the Shapley value for the ith feature represented by phi sub I. This is for a given value or score function V. In this example, the score of the table tennis game is the value function of choice. We iterate over all possible coalitions S that do not contain this feature I. We have a weighting term that depends only on the size of this coalition and the total number of players, capital N. Finally, we observe the change that is seen in the score when only members of coalition S play the game as compared to the score when the feature I is added to this coalition S to play the game. This is the marginal contribution of feature I to this coalition S. Since we are iterating over all such coalitions S and using this weighted term, this is simply the weighted sum of marginal contribution of player I across all possible coalitions. Let us now compute Shapley value for player 1 in this example. First, we take the empty coalition and add player 1 to it. We get 6 minus 0 equals 6. Then we take the coalition with P2 and add P1 to it and note the difference. We get 12 minus 8 equals 4. These are the only possible coalitions that do not have P1 in them. We now use the weighing scheme and compute the weighted sum. This gives us a Shapley value of 5 for player 1. Similarly, we can compute the Shapley value for player 2 by going through the empty coalition and the coalition with player 1. We get a Shapley value of 7 for player 2. Now let us look at what we have. We get a Shapley value of 5 for player 1 and 7 for player 2. So player 2 is a better player than player 1. Also observe that when both player 1 and player 2 played the game, they scored 12. This is exactly what their Shapley values sum up to. Hence, we have decomposed their combined score and attributed individual contributions to both of them to solve their dispute. Let us now get back to explainable AI and see what we have learned so far translates. The game in the context of explainable AI is the prediction task using the black box model. Now, instead of working with scores from a table tennis game, we would work with model outputs. We can use either raw model predictions as value functions or use some performance metric of the model or add causal interpretations to predictions as well. Any of these possible value functions, when used in conjunction with Shapley value-based allocation, will bring with it the desirable axioms we discussed earlier. We will see multiple ways of formulating this throughout the tutorial in different contexts. Instead of these human players playing the game, we have individual features or even data instances that can act as players. These features or data points act as players while participating in the game of generating prediction scores from the black box model. Finally, the payoff allocation now translates to computing Shapley values corresponding to each feature or data instance such that they end up adding to the prediction given by the model. There is one slight hiccup though. When we had our two players playing table tennis, we could send them for a singles game and note their individual scores. However, it is not possible to send partial instances with only the members in coalition to a machine learning model and get predictions from it. We need to find predictions for these partially formed instances, which translates this into a missing value problem. People have tried to solve for this problem in multiple intuitive ways. We will look at two of the most common approaches next. The first way to approximate Shapley values in an XAI setting is through marginal Shapley. The idea here is to marginalize over all features that are out of coalition in S prime. Mathematically, we have the following formulation where members in coalition S are known and set to the values small x sub s while we marginalize over all features in S prime. For instance, let us take a case where we are modeling using two features, education and marital status, and computing Shapley value-based attributions for Rosa. The coalition set here in this case is the feature of marital status, while education is out of coalition in S prime. So we fix the value of marital status to be unmarried, which is corresponding to Rosa's attribute, and then marginalize over education. This results in two instances, P1 and P2, that share Rosa's marital status of being unmarried while having education set to other possible values, specifically master's and PhD. Now that we have these well-formed instances, we can get their predictions by passing them through the model and approximate the value function. This particular way to approximate Shapley values through marginalization was used in quantitative input influence, which was one of the earliest works that sought to use Shapley values in context of model explainability. However, there is one issue here. These instances P1 and P2 may not necessarily correspond to plausible instances. This leads to out of distribution instances on which the model was never trained, and that does not always make sense to the model. Because of this, obtaining model's prediction on these instances will not always give sensible outputs, and this could adversely affect our Shapley values. Another method to approximate Shapley values that does not suffer from this out of distribution issue is conditional Shapley. Here, instead of marginalizing over features that are out of coalition in S prime, we condition on the features that are in coalition in set S. This is the mathematical formulation where we just condition on known feature values in set S. So again, we have the same scenario as in the previous slide. We know that Rosa's marital status is unmarried, and we use this information about set S to condition the dataset on marital status equals unmarried. This gives us the following subset with all well-formed instances. These instances are real plausible instances from the dataset itself, unlike in the case of marginal Shapley. We can now obtain prediction for these instances and know the value function of any coalition S to compute Shapley values. This formulation of conditional Shapley is used in the popular SHAP package. However, there are some issues in conditional Shapley formulation as well. This was pointed out in the work by Elizabeth Kumar et al. The issue is that choosing the players in the prediction game is non-trivial. That is, deciding which columns act as players in this game of model prediction is not always straightforward. Let us consider our current case where we had two features, education and marital status. Now we add a third variable in this setting called higher degree, C, which tells us whether the individual has attained a higher degree post-bachelor's or not. In this specific setting, we can see that this column is actually redundant and has exactly the same information as education A. We can now consider two cases as two formulations of the game. In the first case, we take all three features as players in the game. Well, as expected by the symmetry property, we see that Shapley value for feature B is same as the Shapley value for feature C, which is great and super intuitive. But if we consider only education and marital status as players and just use education as the feature instead of higher degree, since both of them encode the same information, we get counterintuitive results. The Shapley value for marital status in the second game is neither equal to its Shapley value in game 1, nor is it equal to the sum of Shapley values of education and marital status from game 1. It is something entirely different. This presents an important observation that the decision of selecting players in our formulation is not trivial and has consequences on the explanations that we generate. Besides these mathematical issues, there are also human-centric issues when Shapley values are used to generate explanations. First such issue is that Shapley value-based explanations lack actionability. Given that we are able to generate these Shapley values and present them as explanations to the manager of the bank, they do not explicitly attempt to provide guidance on how a user might alter one's behavior to obtain a different outcome from the model. Secondly, Shapley value-based explanations are not contrastive in nature. It has been studied that people do not explain the causes for an event in isolation, but explain them relative to some other event. So, for an explanation to be useful to the user, they should be with respect to another similar user who had a separate outcome from what they had. This will help them to reason about their outcome better. This kind of compare and contrast notion is not supported by the current Shapley value-based frameworks. Computing Shapley values is also a big challenge. Computing exact Shapley values is intractable, and even when they are approximated, it is still not tractable to compute them in many cases. Recent work has shown that only in the case where feature independence is assumed and the model to be explained are simple models like linear regression and decision trees is when it is tractable to even compute the approximate Shapley values. As soon as we go to other models such as logistic regression and neural networks, or remove the feature independence assumption, computing Shapley values becomes sharp B hard. With this, we come to the end of the first part of this tutorial. Next, we will have Sayam take us into the second section, which will be based on contrastive and causal explanations. Thank you.